Okay, if you talk about multi-layer perceptron, this is the arrangements there. Again, we are in artificial neural network. In this chapter, we will discuss about the multi-layer perceptron, a simple multi-layer perceptron. The picture is like this, where you have only a single hidden layer, a single hidden layer. Of course, this should be in between the input layer and the output layer. And then again, this one later we'll discuss again later about how to arrange the matrix there, because again how to label this one, because I will have some example on how to label this one in a meaningful way. So you can identify which W, this W is referred to which network lines there, okay. So because later we need to make sure that we can have a meaningful notation there or labels there, so then you are not lost at that architectures. Okay, we'll talk about that later. Okay, okay, this one is still a multi-layer perceptron, but this one is included with bias. Remember, I just discussed about the B there. When we discuss this one, we we just neglected the bias, the B there. So we assume the B, there's no B in that equation. So that's why in your equation there is just a multiplication between your W and your X, but there's no plus B there. But of course, you can also have that kind of architecture where you also include the bias, like this one. So if you talk about bias, so this mean, for example, this is the network, the network one of your hidden layer. So to find your net there, again to find your net there, now I directly using net there. Your net, for example, I call this as a net H1, because that one is belong to this net is a hidden layer, where the hidden layer of neuron 1. So that's why hidden layer of neuron 1, H1. So net H1 is equal to the summation of your i's there, Wi, Xi, plus with your B there, B1, so BH1 there. So later we will try to make sure this symbol is meaningful. This BH1 is this one, is this line. Okay, this is your BH1. So this one, there's a W 11, for example. So this one is W 21. So 1 1 2 1, and then 101, W 101. So then of course the input for bias is always 1, is a fixed into 1 time B, H1 is become B there. So that's why you make sure this component is not include with this component, because you can see that this one is multiple with 1, but this all W is multiple with their corresponding X1, X2 up until X100. So that's why these components cannot be included inside this thing, because it's not like your previous lecture where you use a theta naught, because theta naught is also I think the theta naught is also here, right? Theta naught, because you assume it's multiplied with 1. So in drawing this architecture, if you want to replace the theta naught with the bias there, then the B there is represented by this line, meaning that this line have their own wake, but the wake is called, not called W, is called B there, and the input is 1. So that's why if you do the equation there, it's like a summation of Wi multiplied with Xi plus your bias B there. And then again the output here, the O here, which is distribute into this many line, O here should equal to O, this one is OH1 is equal to your F, the activation function of your net H1. So this net is going into that as an input of your activation function to get your O there. So that is the notation. Later I will show you the example or the mechanism of a neural network, how actually it had been trained in what we call as back propagation. And again, the back propagation is related to your gradient descent, because the back propagation itself, the unit of or the basic function to generate the back propagation is a gradient descent. Okay, in this part we shall discuss about the activation functions. Okay, I believe that I already give you some exposed to activation, a type of activation function before, when we learn about the logistic regression or linear regression, which is activation function is your F2 in your linear regression or logistic regressions. In this slide we talk about, I just show you some example of the activation function, and even I forget to put several activation function that is not inside this slide. Okay, for example, identity, the one that we use in linear regression, and then sign function, and then we have also I think this is sign function. Sorry, this is sign. This is sign. This is unit step. So of course this one is unit step is for Perceptron algorithms, if you remember the history there. And then of course, because there's no smooth transition there, means that it's a very strict or rough decision. It can be either 0 or 1. That is the disadvantage of unit step function. That's why they introduced to a more smooth transition like this one. Never mind, we will discuss this later, because I think it's better for you to understand the back propagation algorithm first before we can discuss on the detail why from here this one is improving. Actually, the most common one that have been used in if you Google the fact about the activation function, the most common one to be used in artificial neural network is sigmoid function. And then people try to improve that, because there's also a disadvantage of the sigmoid. They introduce you with this tanh function. Okay, you can see that the tanh and the sigmoid is almost similar in shape, but this one is look like a sign function, but in a soft decision. If you talk about a sign function, there should be binary as well. It's either +1 or -1, but it's still the hard decision there. Then people try to introduce with this one, which is a soft decision, or the smooth transition there from -1 to +1. But it might be, this one is a better in terms of the range there. Instead of from 0 to 1, you have a wide range from -1 to 1. So why a wide range is better, we will discuss that later. There's a improvement on that. There's a benefit of that in introduce a wide range of transition. Instead of 0 to 1, you have a -1 to +1. And then the one that I don't introduce yet is what we call as a ReLU there, rectifier unit, a rectifier linear unit. Okay, ReLU is a rectifier linear unit. Recently, this one is the most popular one, especially in deep learning. Okay, previously when there's no deep learning, the one that is the most popular one is a sigmoid, because sigmoid is suitable and a very good activation function in artificial neural network. But when people try to explore the deep neural network, they find out sigmoid is not, or the tanh function there is not relevant anymore, and the one that have a good provide a good result in deep learning is this one, which is ReLU. Okay, this is also advantage on that. We will explain again later. Okay, we will explain about this facts later. Okay, so you can but you can read that. You can read the facts there. Why sigmoid and then tongue function work better because they have zero center. You have a wide range there from -1 to +1, but still the problem is that still the saturation kill the gradient, same as the sigmoid also have the same disadvantage where the saturation kill the gradient, and then that's why it's not suitable to be used in deep neural network or deep learning. So that's why they're using the rectifier unit to do that.